In fluid dynamics, Couette flow is the laminar flow of a viscous fluid in the space between two parallel plates, one of which is moving relative to the other. The flow is driven by virtue of viscous drag force acting on the fluid and the applied pressure gradient parallel to the plates. This type of flow is named in honor of Maurice Marie-Alfred Couette, a professor of physics at the French University of Angers in the late 19th century. Simple, conceptual configuration. Mathematical description. Couette flow is frequently used in undergraduate physics and engineering courses to illustrate shear-driven fluid motion. The simplest conceptual configuration finds two infinite, parallel plates separated by a distance h. One plate, say the top one, translates with a constant velocity u0 in its own plane, neglecting pressure gradients. The Navier-Stokes equations simplify to where y is a spatial coordinate normal to the plates and u is the velocity distribution. This equation reflects the assumption that the flow is unidirectional. That is, only one of the three velocity components is non-trivial. If y originates at the lower plate, the boundary conditions are u equals 0 and u equals u0. The exact solution can be found by integrating twice and solving for the constants using the boundary conditions. Constant shear. A notable aspect of this model is that shear stress is constant throughout the flow domain. In particular, the first derivative of the velocity, u0, h, is constant. According to Newton's law of viscosity, the shear stress is the product of this expression and the fluid viscosity. Couette flow with pressure gradient. A more general Couette flow situation arises when a pressure gradient is imposed in a direction parallel to the plates. The Navier-Stokes equations, in this case, simplify to where is the pressure gradient parallel to the plates and is fluid viscosity. Integrating the above equation twice and applying the boundary conditions to yield the following exact solution. The shape of the above velocity profile depends on the dimensionless parameter. The pressure gradient can be positive or negative. It may be noted that in the limiting case of stationary plates, the flow is referred to as plane Poisson flow with a symmetric parabolic velocity profile. Taylor's idealized model. The configuration shown in the figure cannot actually be realized, as two plates cannot extend infinitely in the flow direction. Sir Geoffrey Taylor was interested in shear-driven flows created by rotating, coaxial cylinders. In his 1923 paper, Taylor reported the mathematical result that accounts for curvature in the flow direction and has the form where C1 and C2 are constants that depend on the rotation rates of the cylinders. It is clear from this equation that curvature effects no longer allow for constant shear in the flow domain, as shown above. This model is incomplete in that it does not account for near-wall effects in finite-width cylinders, although it is a reasonable approximation if the width is large compared to the space between the cylinders. Generalizations of Taylor's basic model have also been examined. For example, the solution for the time-dependent startup process can be expressed in terms of Bessel functions. Finite width model. Taylor's solution accounts for the curvature inherent in the cylindrical devices typically used to create Couette flows, but not the finite nature of the width. A complementary idealization accounts for finiteness, but not curvature. In the figure above, we might think of the boundary plate and the moving plate as the edges of two cylinders having large radii, say n, respectively, where is only slightly greater than. In this case, curvature can be neglected locally. The physicist-mathematician Ratibberger reported a mathematical solution for this configuration in terms of a trigonometric expansion. Wendel's result. For physical devices, actual coaxial cylinder devices used to create Couette flows have both curvature and finite geometry. The latter gives rise to increased drag in the wall region. A mathematical result that accounts for both of these aspects was given only recently by Michael Wendell. His solution takes the form of an expansion of modified Bessel functions of the first kind.